Alright, so we are going to do the iChem lesson sort of the old-fashioned way. I'm going to just record myself writing instead of embedding a little presentation inside of another presentation until I get this smartboard situation figured out. So, bear with me. We're going to talk about solution stoichiometry, that good old stoichiometry. iChem Lesson 19, Unit 8. Make sure you have your viewing guide handy. Probably a periodic table would help you follow along as well. Okay, so we're going to talk about using molarity, which we learned and used today, as a conversion factor. So dimensional analysis, we know, uses ratios to cancel units and calculate answers. We have some ratios we've already used. We've already used the molar mass from the periodic table. We've already used the mole ratio from a balanced equation. And then in the last unit we started with this mole to energy ratio from a balanced equation as well with the delta H value. We're going to add one more ratio, and that's going to be the moles of solute to liter of solution, or also known as molarity. Let's start with this example. You want to know what volume of a 1.5 molar solution of hydrochloric acid is needed to react with 21.5 grams of sodium hydroxide. Keyword here being react. This tells you that it's a stoichiometry problem because you have a reaction. So the very first thing I need to do is write my reaction equation. I have hydrochloric acid reacting with sodium hydroxide. Okay, this is an ionic compound and another ionic compound, so it'll be a double replacement reaction where I have hydrogenous plus 1 is going to combine with hydroxide, which is minus 1. That's just water, HOH or H2O, whichever way you want to write it. And then I have sodium and chlorine, which are going to combine together. Sodium is plus 1, chlorine is minus 1, and NaCl. Okay, now that I have my reaction, I can use dimensional analysis to answer the question. So I want to react this solution with 21.5 grams of sodium hydroxide. So I'm going to start there in my dimensional analysis. Eventually, in the end, what I want is volume of hydrochloric acid. Volume in terms of molarity is in liters, so in the end of my dimensional analysis, I'm going to get liters of hydrochloric acid. Starts off the same old way we've been doing it. I have grams of sodium hydroxide. To be able to use my balanced equation, my reaction, I need moles of sodium hydroxide. This ratio right here should look familiar as your molar mass. I look up on the periodic table and I find sodium to have a molar mass of approximately 23. Oxygen is 16. Hydrogen is 1. So if you add that all together, you get 40 grams per 1 mole. Okay, now that I have moles of sodium hydroxide, I want moles of hydrochloric acid. See, I have hydrochloric acid over here. So I'm going to use a mole ratio from the balanced equation. The math is simple here. My balanced equation, I have 1 hydrochloric acid for every 1 sodium hydroxide. Finally, I can use my molarity. I have moles of hydrochloric acid. I want liters of hydrochloric acid. Now, what is this new ratio I have? Well, I have molarity. If I want to write that somewhere off to the side, maybe down here, if I translate what the capital M molar means, it means I have 1.5 moles per 1 liter. So I can translate this ratio into my dimensional analysis. I have 1.5 moles per 1 liter. And just do the math the same way as always. Multiply across the top, divide across the bottom, and I end up with 0.358 liters. This small number, point something liters, makes a whole lot more sense to report in milliliters. So if I multiply this by 1,000, I get 358 milliliters. So the reaction told me that I was going to have to write a balanced equation and do dimensional analysis, stoichiometry. I introduce here this new ratio, which is just my molarity, taking that big M, capital M for molar, and translating that into what I know about the units. Let's do another example. What is the molarity of a solution of hydrosulfuric acid if 48.5 milliliters are required to titrate 35.6 milliliters of 0.35 molar iron hydroxide? Okay, titrate here, it's hidden, but that's another word for reaction. In terms of acids and bases, we'll explore these in detail next week. But in general, I'm going to start the same way as last time. I have my reactants. I want to form my products. Hydrogen combines with hydroxide. Iron combines with sulfur. Okay, hydrogen hydroxide, we know that that is water. Iron and sulfur, we need to be careful here. Iron is a transition metal. We don't know its charge right off the bat, but if we look here at the subscript on hydroxide, that tells us that the charge on iron has to be a positive 3 for it to balance out the 3 minus 1s for hydroxide. So I have iron 3 and sulfur, which we know to be a 2 minus. So when I swap and drop, I get Fe2S3. Now what is left is for me to balance this equation. I have 2 irons, I want 2 irons. I have 3 sulfurs, I want 3 sulfurs. That leaves me with 6 hydrogens and 6 hydroxides. That means 6 waters, because remember, water is also written as hydrogen hydroxide. Okay, so now we're ready to do the stoichiometry, starting with what I know. The solution I know the most about is this iron hydroxide solution. I know that I have 35.6 milliliters. I also know that molarity is in units of moles per liter, so I want this in liters before I can use it. So divide by 1,000, I get 0.0356 liter. That's where I'm starting. Of iron hydroxide. Alright, now, again, I have liters. Just as before, to be able to use my balanced equation, I need to have a number in moles. So I have liters. I want moles. Moles per liter you should recognize as molarity. If I translate this into moles per liter, I would put 0.35 moles per liter, per 1 liter of solution. So that ratio actually just goes straight down here, 0.35 moles per 1 liter. The last step to the dimensional analysis is use my balanced equation from how many moles of iron hydroxide, how many moles of dihydrogen sulfide would you use? Okay. Hydrosulfuric acid. These mole-to-mole ratios come from the coefficients in the balance equation. I have 3 hydrosulfuric acids and 2 iron oxides. I'm going to stop here in the dimensional analysis and just get moles from this. Okay, so I multiply across, divide by 2, I end up with 0.187 moles of hydrosulfuric acid. Okay. Now I have moles and I have volume. Not in liters, which is what I want. Divide by 1,000. I have liters. Remember our molarity triangle here. We have moles. I want molarity, cover it up, I do moles divided by liters. So I'll do 0.187 moles divided by 0.0485 liters and end up with 3.89 molar hydrosulfuric acid as my answer. So again, I started with a reaction equation, a balanced reaction equation. Started the dimensional analysis with the solution that I knew everything about. I introduced molarity again as a dimensional analysis ratio of moles per liter. Found moles, and I used the definition of molarity, moles per liter, to calculate the molarity given the volume. Alright, last example. White precipitate forms when 200 milliliters of 0.2 molar potassium phosphate reacts with calcium chloride solution. What mass of precipitate will form? So I have potassium phosphate, calcium chloride, reacting to form potassium chloride, that's K plus and Cl minus 1:1, and calcium, which is 2 plus, and phosphate, which is 3 minus. If you don't remember those, you could take them directly from the formula, backward swap and drop. Calcium, phosphate, swap and drop, I get Ca3, PO4, 2. Okay, last needs to be balanced. I have I have 3 calciums. If I put a 3 here, I'll end up with 6 chlorines. If I put a 6 here, I have 6 potassiums. If I put a 2 here, I have 2 phosphates. 2 phosphates, 2 phosphates, unbalanced. Alright, now on to stoichiometry. Let's start with the solution I know the most about. I have 200 milliliters, that's 0.2 liters. Of potassium phosphate. I want moles to be able to use my balanced equation. Moles per liter you should recognize now as being the units of molarity. Over here I actually have 0.2 moles per 1 liter. That's what the molar tells me. And I want, now what do I want actually? I want to know the precipitate. That's the solid. which one of these will be solid? Let's think about our solubility rules. Potassium. So on that first rule, potassium is an alkali metal. It's always soluble, so this would be aqueous. Phosphates, always insoluble except for some exceptions. None of those are calcium, so that's my solid. Alright, so I'm looking for what's the mass of calcium phosphate. So I want moles of calcium phosphate. And I have moles of potassium phosphate. Okay, these come from the balanced equation. I have 1 mole of calcium phosphate for every 2 moles of potassium phosphate. In the end, I want mass. Well, I have moles. You should recognize grams per mole as molar mass. I have 3 calciums. Each of them are molar mass of 40. I have 2 phosphorus, and 8 oxygens. You add that all up, you should get 309.8 grams per 1 mole. As always, multiply across the top, divide across the bottom. I'll get 6.196 grams of calcium phosphate. Okay. Again, starting with my solution that I knew everything about. If you're given volume and molarity, you know enough to be able to find moles and use the balanced equation. I used molarity again as a ratio within my dimensional analysis, and everything else the same as we've been doing for a while. Don't forget to complete the Google form. I will see you tomorrow.